Welcome everyone for another UKZN art seminar. And today our speaker is Lukas from Imperial College London. He's working on machine learning, cosmology, and he's gonna give us talk about the work he's been doing recently. Thanks, Lukas. You can go ahead.
Thanks, Ajit. So the disclaimer I was giving Ajit before some of you logged on is this is sort of a Frankenstein presentation of some of the projects I've been working on, but I think it sort of wraps this specific project. I know a lot of you are working on radio astronomy and cosmology. It will wrap what we're doing in terms of mitigating systematics like foregrounds into what I consider sort of a more global view of science in general. We can wrap it up in this thing called simulation-based inference. So I'm not sure how many of you folks have worked with direct SBI methods, but I would hopefully give an overview of how it all sort of folds together. So broadly, I work on sort of late stage cosmology. I'm nominally a cosmologist. Most of my day-to-day is working on simulations and then working on statistical techniques, a lot of the time using neural networks to make our data talk to the theory we care about, and then eventually to the actual data we collect. So it's getting everything sort of married together. So this is sort of, again, this is probably the simplest way I can write down what we're doing. Or I think regardless of how you spin it, most science is a Bayesian problem, and especially if we're dealing with things like astrophysics and cosmology, the classic thing to say to motivate Bayesian statistics is that, well, we've only got one sky, right? So we observe the universe. We've come up with some very descriptive models to describe, the creation of large-scale structure, which can be whittled back to the CMB, which can be whittled back to the Big Bang, and all of these templates or models for this data that we see are governed by a set of scalar parameters or maybe by a space of models, and the interest of our whole intersection is figuring out which models best describe the data. So this is really, so again, whether or not you like to think with a frequentist hat or you like to think with a Bayesian hat, we are fundamentally interested in this Bayesian inverse problem. What is the probability of a given parameter or model being a good description of this data, this mutable data that we see? And so the way you write it down, we do this in your first stats class at uni. You write down Bayes' rule, you just factor over it, and you just move the evidence over. So Bayes' rule, top to bottom, is these data likelihood times the prior over theta, this model parameter you care about, divided by the evidence. Most of the time, we can the hardest part, or most of science, at least the science we do, is coming up with this modeling, this likelihood. It's like, how do you measure the distance between your model, which outputs X, and the theta that you care about, the model parameters. So most of cosmology up till now has been done using explicit inference. So again, without going through any math, the reason why the CMB folks got so lucky, well, I'd say lucky, the reason the CMB analysis works so well is that the CMB is a pretty Gaussian sky, and we can test this. We've got some really good theoretical predictions for why it should be Gaussian. But what's amazing about the Gaussian distribution is that we can write it down. And of course, the CMB is a scale-dependent Gaussian, so that becomes controlled by the power spectrum, or in the explicit case of the CMB, the angular CLs, and you can fit that template to the data exactly. So that's an explicit likelihood inference problem. We can do an MCMC chain because we know with the log probability relating X and theta. Here, theta control those power spectrum amplitudes and such. But in implicit inference, all of science is really implicit inference, because you can come up with a model or a simulator for data. Again, we see an apple fall from a tree. We say, okay, Newton said, okay, that looks like F equals ma. And these days, we would probably forward simulate an apple falling from a tree with a bunch of different computational models. So if you can write down a model or in fact a simulator, then you have yourself the likelihood, because you're relating some sort of parameters of the problem to the output of the data. But then the question becomes, okay, how do we put this on a firm theoretical footing? And also how there are some engineering concerns. It's like, okay, well, once you have the data, how do you compare your simulations to the real observed data that you see? So this sort of puts everything together. So I'm going to hop over to the iPad now, because I think this is best done sort of by hand. Slow down. So I'm going to start broadcast. It should come up in 3, 2, 1. Okay, you should see that now. We'll go here. So I just kind of wanted to take a breath and like write down exactly what's happening here. So we're interested in the probability of our model parameters given some data X, and we wrote down Bayes' rule. It's just the likelihood multiplied against the prior. And so, but what does this look like in the case of simulation-based inference? Well, I don't know if any of you folks have worked with Bayesian hierarchical models, but I find that this sort of plate diagram structure is a really good way to visualize everything that's happening. So in the case of so we put a theta up here. Theta is a random variable, right? Theta is varied over the prior. That's what this first line is saying. Theta goes into some sort of model. Like I'm gonna write down the very simplest flow chart here, and your model spits out X, right? So, and in the plate diagram situation, circles are random variables, and the boxes are deterministic things. So this is the simplest model you can write down. And in this case, your model becomes your P of X given theta, right? Because you've chosen theta, you put in that chosen version of the random variable, the model takes in that number and spits out another set of numbers. But models can be made far more complicated, as we know. You can have things like systematics and birds that fly in front of your telescope. And I heard recently that there's a massive problem with 5G towers or something with the SKA. So lots of other systematics. So you can put systematics in. There's another random variable that maybe you don't care about. So then, oops, sorry, just lost my. There we go. Let me know if you can't see it. So again, all we're doing is we're just translating math into pictures. But what you can do, what you'd like to do, is marginalize out all of this, all of the nuisance parameters that you don't care about. So you could integrate them out literally just by ignoring them. But again, the usefulness of this sort of simulation-based approach is that you can fold anything you'd like into the model, as long as you're varying the things that if the things that you don't care about are varied enough such that the model incorporates them when outputting this number at the end here. This is effectively marginalizing out a parameter. So in an MCMC case, right, you would do this integration explicitly. You run your chains, you propose all of these different random variables as dials that you could twist to get your posterior as close as possible to your target log density. But then you throw out all the chains that you don't care about, and at the end of the day, you just choose, maybe you choose 1 or 2 thetas to present as a triangle plot, right? That's what, if you've looked at some of the like CMB papers, this is sort of the trick of behind the word marginalization is just throwing it away. Okay, cool. So we sort of translated this into a nice plate diagram, and if you believe my sketchy demonstration here, all of this can be sort of folded into the same vocabulary that we use to describe normal explicit inference techniques. But now the question becomes, okay, so now you've got your data X, and what does this look like in practice? Like how do you actually report? How do you get from this forward model to something like parameter constraints? Like how do you grade how good your model is against your data? Well, you can. So this is probably the most generic representation of Bayes' rule that you can come up with. So let's say you've got your data X on one axis, and you've got your theta on the other one. And in this case, X and theta, I've drawn them as vectors, but here, let's just call them one number, right? So you put your theta and maybe you have some nuisance variables, eta, throw them into your model. One number gives you one number, and that's what you want. That's the relationship you want to probe. Okay, so, and let's just say on the side here, you have some X observed. So this is just one number that you've it's an observation you've taken, and then you've gone back and tried to write a description of how to get from theta to X. Cool. So what you're going to do is you're going to choose a bunch of thetas from the prior again. So up and down this y-axis, and then you're going to simulate a load of x's. So maybe 1 theta, you'd get an x here. If you chose a theta down here, you'd end up with an x there. And then if you continue simulating, maybe there's some scatter. Maybe this is controlled by that eta parameter that you don't care about. You might end up with some relationship like this. So you end up with some sort of banana-looking thing. Okay. But then you have this X observed, and if you've done the whole blinding thing or whatever that cosmological experiments do, maybe you take the curtain off, you reveal it, and X observed ends up falling right here. So then what you do, okay, so again, it's just one number that we're looking at. Along the x-axis, you say, okay, I'm going to, so that the simulations that best describe my observation are within some epsilon ball of the truth. So in this case, this width here is like 2 epsilon. And this is sort of a hyperparameter you can vary. But if you collect all of these points and the thetas that correspond to them, you'd end up with, if you just do a plot, so this is going to be P of theta given X observed, your distribution, your posterior will look hopefully something like that. I don't know. Don't actually try to create a density from the points I've drawn. But this whole process here, this manual process that you can look for one, one dimensional data and one parameter you can literally do on a piece of graph paper, is called approximate Bayesian computation, or ABC. And this is I think this is probably the best way to describe Bayesian statistics and the Bayesian school of thought. Is again, you have this immutable X, you've come up with some process to describe it that gets close, you simulate it a bunch of times, and you select the simulations that get close to the data. Now, okay, so this motivates two things. One, it motivates designing good simulations. And now we have sort of, a framework with which to use simulators in a, and kind of an automatic way against data. But two, it raises a really important question. Is, okay, what happens when your data and your parameters are no longer one-dimensional, right? What happens when X is actually, are really, really big? So this motivates using compression techniques to get you to a smaller subspace and cleverer statistical techniques to come up with ways of representing the data in this framework. So okay, I just wanted to sort of take a second to look at this. Before I move on, I just wanted to redraw this diagram here, because I mean, I know at least Ajit and Kavi work on HIRAX and radio telescope type projects, which are again limited at this point by things like foregrounds and systematics. What's really cool about the simulation-based inference framework, and I'll get to a very specific example of this, is that it gives us the framework to test models and sort of model robustness. So in the case of 21 centimeter foregrounds, right, we had this diagram from before. You have some, well-founded cosmological model for whatever, maybe it's structure formation, maybe it's bubble growth, whatever observable you'd like to relate to your model parameters. But unfortunately, in the way, you have something like foregrounds, which obscures the actual the unadulterated data that you'd like to see. So this ends up being X hat. What I'll talk about sort of at the end of my talk is introducing a new layer in this. So I'll just show this as a flow chart here. A new layer, which again is this case, it happens to be a deep learning technique that helps remove the foregrounds to give you sort of, let's suppose, X clean, which hopefully looks something close to what we think the true underlying data looks like. But we will never actually see this clean, unadulterated sky beyond the foregrounds, right? So this is sort of like, if there's some true value, some true model parameters of the universe, some true forward model that gets you there, we will never actually know what numbers were chosen by some omniscient being. But we can, in this framework, have, again, what we think is a relatively decent observation. So you've got X observed with a hat. You can clean it to make it X clean observed. And then you can compare this forward simulations to the observed sky that has been processed in the exact same way. So anything that you do to your observed data, you'd also do in your forward pass of the simulator, because that you can basically put everything that happens in reality in the forward pass, and then write down some sort of distance criteria in a way of distinguishing the simulations from reality. And that's what I'll get to in just a sec. So let me unshare my screen. And hop back over to the PowerPoint. Also, please feel free to interrupt me with any questions. I think I kind of wanted this to be a bit more sort of informal, and put everything, because I'm as I said before, I'm sort of concatenating two different sides of my research here. So if anything's unclear, or you're not familiar with some of the notation or whatever I use, then do let me know. Cool. So right, so this slide is exactly what I did by hand, where you're looking at approximate Bayesian computation. You're trying to get your your simulated data to look like the real data that you collect. And essentially this red slice, or sorry, this blue slice is the slice of the observed data that you collect. and then you just take simulations that are close to it to construct some sort of posterior density. So again, this is just a way to put everything into a framework. And this is sort of what I showed in plate diagram form, is that you have some you draw from some prior, you shove in your different values of theta into maybe the same simulator, maybe it's different models entirely, depending on what you're interested in simulating. And you end up with a load of simulations. And here they're summarizing the simulations by the mean of this output distribution. So they get a load of points that create these curves, and they take the mean of it. And then they say, okay, if the mean is close to my observed data, which they just call mu here, then you accept the parameter that generated that simulation, and you construct this posterior exactly as we did by hand on the piece of graph paper. So what's very cool about this framework is that it's sort of, I said cosmology here, but it can literally be really any science now that we have computers to help illustrate our theories and explanations of data. But it can all be written down as an optimization problem. And one such thing that you can optimize is exactly how you would compare your simulations to your data. So by framing cosmology this way, you might say, okay, if I've got a simulation of large scale structure, I know that because the CMB responds really well. The CMB is controlled by a power spectrum. Large scale structure should be largely controlled by a power spectrum, but there might be some more information beyond, because gravity is generated what we're pretty sure is not a non-Gaussian field. So you might say, what extra information can I extract from the field in order to better compare my simulation to my reality? So that's one thing you can do. And again, at the end of the talk, you might cast this optimization problem as, what is the best network that can separate foregrounds from cosmological signal that gives me the best constraints on cosmology, the parameters are varied, or gives me the best map, data reconstruction, again, of that latent variable that I alluded to. So just think about it as, because we can do this automatically, we can use technology like machine learning in order to fit for these criteria automatically using simulations. So one thing that I work with, again, this is just a metric of informativity, or how good is your model at spitting out data that looks like what you care about. The Fisher is just sort of the curvature of the log of the likelihood. And at the beginning of this talk, I considered theta to be very small. Again, in lambda CDM cosmology, the things that we want to infer are usually 4 to 6 dimensions, like 4 to 6 cosmological parameters. And before projects like Planck and even SKA get greenlit, somebody has to sit down and, again, a lot of the time using an explicit form for the likelihood, which is in this case curvy L, write down what the Fisher forecast. So how, if we collect yay much data, how much will it tell us about this particular model? Because otherwise, you wouldn't if we didn't have this notion of information, we wouldn't have any foresight as to what we'd learn from certain cosmological probes. But explicitly, this is the curvature of the log likelihood, which is that P of X given theta. So again, if your model, your simulator, is really responsive to the model parameters, you'll have a very, very tight log likelihood. And if it doesn't describe the data very well, then you'll have a much wider constraints. You'll have a much more diffuse distribution. And this is formalized. Again, this is just sort of a notion of like information. This is formalized using the Cramer-Rao bound, which tells you that the Fisher information with curvature, the likelihood, is the lower bound of the variance of an estimator for a parameter. So it tells you like sort of how the best you can do for a certain parameter. Again, in some other work, I use this as an optimization objective. So you can literally write this down. You can write this down in a simulation-based inference setting, and then ask that you maximize the information. So again, make the likelihood as peaky as possible, and tune some neural path mapping to get that metric as tight as you can. So this is formalized as information maximizing neural networks. And again, this is just that flow chart that I did out by hand in fancier graphics. And this motivates. So here, what we're interested in learning is some sort of compression. So the data D is far too big to deal with as D. So we'd like to learn some sort of mapping down to some smaller summary space X, which is hopefully a lot smaller and like the example we did by hand. So a neural network is a learnable path, a learnable function down to some smaller summary subspace. And if you can, for this case, we write down the Fisher matrix explicitly for these summaries using a specific set of simulations. This compression network then becomes part of your likelihood that you can tune to your problem. So again, this is just an example of how you can throw, you can use that sort of formal vocabulary that we just developed for this problem, and write it out and explicitly optimize on what we'd like. In this case, it's this compression mapping. And this hones in on another thing on my to-do list, is that you know, if I start a talk, or if I meet somebody new who's who's not worked with machine learning or anything, and I start by saying, oh, I work on machine learning methods for cosmology, the first thing I've seen, and I can see it in conversations I have with people, the sort of skepticism lights up in their eyes as soon as I say the word machine learning, before you know, explaining this framework or this theoretical background, because again, machine learning used blindly, as we'll see for the foreground stuff, is not super useful for anyone. So this particular project that we worked on, again, that explicitly maximizes information and learns some sort of mapping from, you know, cosmological fields down to a couple of numbers, we can show that the compressor has captured all of the relevant information by testing this technique on cosmological simulations with known likelihoods. So this is one of the first projects that I worked on, showing that for a Gaussian field, again, we can describe it fully by its power spectrum, and more specifically, all of these pixels have Fourier components if you take the transform of the fields, and that fully describes the information content of these fluctuating pixels. And those pixels fluctuate according to some parameters A and B, which control a power spectrum that we threw together for this toy example. And so we can do this analytically. So we can write down the form, and we can integrate the entire, we can sum up all the log probabilities of all the pixels, and then you get this orange curve. But then we can also feed it to that neural network, optimize the neural network to spit out maximally informative numbers. In this case, it's just 2 numbers per field, and then do that accept reject. So I didn't do it on graph paper. You can do, I did it automatically, but you can almost do it then if you had a load of them and you could write out the coordinates on graph paper, accept and reject those simulations to construct this purple contour, which lines up perfectly with this nice analytic likelihood. So what we show in this example is that a neural network can learn to capture all the statistics that you care about with respect to the thing that you're optimizing on, which is in this case just A and B that we wanted to know. But it means that again, wrapped into this theoretical framework, you can write down criteria that can be properly evaluated. And then if you care about the information content, this is what the learning curve looks like for the network. Okay, cool. So that's sort of the this is like probably this is just sort of a good check to know that a lot of that neural networks can be useful for in a very formal setting. What's cool is you can take this even further, which we've done not that recently, using the same exact framework, but now we can operate on things like graphs, which are just weird, ragged structures. But we do have neural networks that can consume these weird, knobbly networks of points. In this case, this happens to be a load of dark matter halos connected by distances. And all of those, the dark matter halos, their masses, and the distances between them tell us something about cosmology as well. And we can wrap all of that together into, I forgot to delete some slides here, sorry, into the exact same forward path. So again, the network that talks to this weird ragged structure becomes part of your likelihood, and you can optimize it to tell you what changes in the graph structure, what changes in the data, tell me the most about the parameters that control them. So that's what we're interested in there. Okay, so hopefully I've convinced you now. I'm at the little over the halfway point. I've convinced you that neural networks are decent tools for taking outputs of simulators and are learnable functions that you can wrap into this simulation-based inference framework. I'll also, this is a good point to stop and ask if anyone's got any questions about SBI in general. I'd be happy to go back through some of the formalism, because then I can move on to the 21 centimeter stuff. If not, then I'll keep going. Okay, and then I've got a couple more summary slides that tells you in this graph setting exactly we're able to pull apart the network and say, okay, this information is coming from halo masses, this information is coming from clustering. We can compare it to existing statistics. So again, this is sort of an effort of diplomacy to show that okay, you can use networks in a cosmologically compatible and meaningful way. So that's what the next couple of plots show. Okay, so now this very old slide of mine, but now we can move on to 21 centimeter cosmology. So everybody here is probably relatively familiar with this, but it's a new, hopefully a complementary probe that stretches further back in cosmological time for measuring the growth of structure, and before that, the interesting physics of the epoch of reionization sort of get us from CMB to now. But obviously, as we all know, the big issue in 21 centimeter cosmology is the foreground contribution of the galactic plane, synchrotron, point sources, and other nonsense that happens between us and the cosmological sky beyond. And unfortunately, these foregrounds can be what is the 3 to 5 orders of magnitude bigger than the interesting cosmological signal underneath. So this is this becomes an issue for any downstream analyses of this data. So from my understanding, this is still the status quo. There are lots of variants of foreground subtraction, or sorry, blind statistical projection out there, but principal component analysis, PCA, is generally considered the status quo. And in the case of foregrounds, so if you look at sklearn or any online documentation of principal component analysis, a lot of the time you're trying to look for the most meaningful features. So the best way to look at PCA is sort of take a look again at a Gaussian distribution that we know and love. Here it's plotted in, I've got a 2D Gaussian distribution for two variables, x1 and x2. And this data happens to be, if you take a look at the semi-major and semi-minor axes of this blob of points here, you can see that there's the most variance, the most variability is explained along this principal axis, and the semi-minor axis is the direction of less variability. So what PCA does is finds the directions of like most of highest variance in the data. So the idea is for sort of image-based techniques, when you have a bunch of pixels that are lighting up, that may or may not carry, they may or may not be displaying a picture of a cat or a dog or a bus. The reason PCA works so well for natural images is that things like picture borders, which tend to be really a lot darker, but also a load of pixels that are lighting up in one line will be very, very different in terms of their intensity or their values from pixels on either side. So PCA works as a good way of decomposing images, for example, because it literally, all it does is it goes and does an eigenvalue decomposition of the image, the massive space. It flattens everything out, computes the eigenvalues of that flattened out piece of data. In this case, this is just two-dimensional, so it just flattens it out into one vector. Computes the eigenvalues, and then it orders all of the eigenvalues, biggest to smallest, smallest to biggest, depending which way you want to go. And those eigenvalues usually correspond to the most variable features of the data. And the projection, what's learned as a result of this PCA decomposition is a projection V from your image space down to your PCA space and back, which is mediated by these eigenvalues. So in the case of PCA subtraction for foregrounds, the foregrounds are literally considered to be this semi-major axis, right? Because they're big, they're relatively smooth in frequency, they carry the highest weight in the eigenvalue decomposition. And then if you remove the first couple of them, you're left with some residual signal. Again, in this second panel, all the points have been collapsed down into this second dimension here, again, along this semi-minor axis. So this is what's happening at level of millions of pixels in a PCA cleaning of a sky. So, and I said, okay, this is the thing is, okay, this is guided by how we think the physics works. And we have decent observations of galactic synchrotron and decent observations of, what we think the cosmological signal underneath looks like. But that interface between foreground and cosmology is not guided by physics. So and PCA is a blind mediator between essentially consider there's a handoff at a certain point in eigenvalue space between cosmological and foreground signal, and PCA is completely agnostic to physics in this case. Cool. What this looks like in the case of 21 centimeter data is, so what you can do, again, you can decompose the whole thing and do the eigenvalue decomposition, sort the eigenvalues. In a case where so the best case scenario where the foregrounds and the cosmological signal are very, very well disentangled, you have the eigenvalues, which these massive eigenvalues, which are inhabited by the foreground signal. And then if you follow along this, let's say this red and blue line here, you get down to an eigenvalue number of whatever 6 or 7 in this for this particular set of simulations, and then the eigenvalues themselves don't change very much. So what the takeaway from this plot and the conclusion from this paper is that if you have a set of simulations that do this, you know that your cosmological signal starts at about an eigenvalue of 6 or 7. So if you remove all the first bit of the first 7 eigenvalues, you should be, reasonably fine. But again, this is completely agnostic to the physics. And what this paper by Alonso et al. In 2014 shows is that if you change things like polarization in your foregrounds, the contamination between the distinguishability between foreground and cosmology becomes almost incomprehensible. So if you increase the correlation, decrease the correlation length of polarization for foregrounds, that ends up bleeding all the way into the cosmological signal that we thought we could subtract initially. So again, this motivates figuring out some mediator. Hopefully learn from simulations, that's something that can encode the physics about this separation of foreground modes and cosmological modes. Okay, yeah, so you can stop there. So this is a technique we put out a little while ago now called Deep 21, which is an image-based network that seeks to do exactly what I said, but in image space. So you take your foreground contaminated sky, you pass it through your PCA, and again, you have no idea whether or not you have mostly cosmological signal or mostly foreground signal and where that boundary is. But you just say, okay, I'm going to take out 3 to 6 components because that works for my existing model. Then you can pass the residual through a network trained to predict the true underlying signal. So that's what this little cosmological box is here. So what the network takes in contaminated skies and does its best to reconstruct the underlying cosmological signal. And in this particular paper, we just did this for fixed cosmology and fixed foreground template. So it doesn't encode any of that notion of sort of simulation-based inference, but it is a technique that is trying to encode some information from simulations. So what happens when you train a massive network like this, and again, don't worry about all of this, all of these particular labels in the middle, but what happens is what's happening under the hood is that this network is capturing what meaningful fluctuations in this input cube, this input set of input voxels, what patterns tell me the most about the underlying cosmological signal. And the only way it learns that is by seeing loads and loads and loads of examples from some set of prior simulations. Right. So again, for this particular fixed suite of simulations, we were able to show that, okay, this network does a decent job at reconstructing the signal from the residual, thus sort of re-encodes the physics that we might have lost, or removes more foregrounds, depending on how you look at it, glass half full, glass half empty. And again, you can take a look at the residuals if you care. Everything, and then the power spectra of your particular direction. In this case, we looked at angular and K parallel happen to be reasonably reconstructed as well. So we don't lose interesting clustering information from when we operate at map level. Okay, so then in the last 5 minutes, I'll talk about what we're doing with HIRAX and how we're sort of going to combine the two different notions. The one sort of more, let's say, the theoretical footing that we put this problem on in the beginning, and then sort of this more data-driven foreground separation that we did with Deep 21. So HIRAX is now an IR telescope. So we're not looking at single dish. So Deep 21 was based on single dish simulation. So now we've got an interesting complex signal. And what we're interested in at the end is eventually reconstructing decent delay spectra. But the problem remains that the problem is identical in that the foregrounds are messy and they're massive and they get in the way of the interesting signal underneath. So you can kind of take a look at this I guess I don't have the color bars here, but the order of magnitude is still the same as before. And again, you can and what's interesting is if you look at the eigenvalues taken from a PCA decomposition of one of these simulations, we can see that the foreground signal bleeds together a bit more with the cosmological signal than we looked at previously. So if anybody looking at this plot who knows what's happening under the hood should be, if you're interested in doing science with the clean maps from HIRAX or from SKA, this should make you nervous if you're relying on PCA, because where does foreground stop and where does cosmology begin? Again, it's a softer transition between the two of them. Where is the stopping point? And this is also beam shape dependent, which in our case will be sort of a variable. It'll be a combination of a couple of different shapes, and that's something that we can best describe in a forward modeling sense. Okay, so that again sets the problem. And again, this is a comparison to the single dish theory paper plot before. So again, moment networks is a way to wrap in the notion of simulation-based inference to this map reconstruction. So in the case before with like parameter inference, we were interested x and theta were relatively small. Now maybe theta, let's keep theta small. So theta can be, let's say, a cosmological parameter, and in the case of HIRAX, we're going to be varying h naught. And you can also come up with some other parameters to vary BAO or whatever feature you're interested in. And then x here is going to be massive. So x is this delay spectrum output that we get from our simulations that we're hoping to operate on and make clean from foregrounds. So what we can employ is sort of Deep 21, but now done over a prior, or in this case, a joint distribution of a bunch of thetas, parameters we may or may not care about that we're varying, and the varying realizations of data that come from them. And if you minimize, or maybe in this case, okay, take theta to be a clean map. So we want x is a dirty map and theta is a clean map, but we still have them from some massive distribution of simulations. If you try to minimize, if you try to do a mean square error, which is what we optimize Deep 21 on, over this distribution, what you're really getting back is a posterior mean over this full joint distribution. And if you do, and then if you learn a second moment, so you fix that network that gave you a decent clean map, and vary under another squared loss, with another network operating on the same dirty data, you end up with a second moment, which is this posterior variance. So what we can do, and this is what Jeffrey and Wanda, some of my collaborators, did with CMB foregrounds, is you can reconstruct a clean map as well as an error bar for that clean map. And this is, again, if you're interested in doing downstream tasks, like coming up with summaries and such for this, for the experiments, you should breathe a sigh of relief that there might be a way forward from these, cleaning techniques using simulation-based inference. So the idea in HIRAX is that we do the same thing we did in Deep 21 and try to get a network to spit out clean data maps, but now we have a way of probing uncertainties in that pixel by pixel reconstruction, which is sort of a step beyond what's previously been done. So I'm only showing first moments here, but what you can see is that so again, PCA, this is operated on a single simulation, but you can see the unit at first glance looks similar to the PCA, but if you take a look at some of the summary statistics, we see that again, this is also with this is a very minimal setup at the moment. So it's not, the network's not been trained exhaustively as it had in the previously published case, but we see marked gains across these K parallel modes that again would not be possible to improve beyond the PCA in an interpretable fashion. So again, with PCA, you have one sky. If you operate on it with PCA, that's your sky, and you have no idea whether or not there's you've got foreground contributed to the reconstructed signal. Thanks, Kavi. Thanks. So this is where we're going, and again, we're wrapping it into a more a framework with a firmer footing than some of these one-shot or very sort of trendy deep learning papers might have done 2 years ago. And I say that as somebody who's published one of those before. So this is sort of a marriage of not two schools of thought, but trying to fit foreground cleaning into what is ostensibly a massive simulation-based pipeline. I can stop here since we're only 3 left. I'm not sure if you guys had any questions or anything.